Hello, my name is Sean Bell, and I'm a research scientist at Facebook AI. I'm excited to be able to present some of our work in product recognition at Facebook. This was a collaboration involving many researchers and engineers across multiple orgs. In this talk, I'll give a brief overview, spend most of the time on architecture, and then cover some experiments showing some of the gains from our new system. Product recognition systems have several basic steps. First, you need to identify where all the objects are with object detection. Then you extract features for every box, which can be categories, attributes, continuous embeddings, hashes, or a combination. Finally, you compare these features against a large-scale index to retrieve and rank the most likely matches. In this example, we're only showing one result, though a real system would give a ranked list of guesses. This talk will focus mostly on training a better computer vision trunk to extract features and other aspects of an image. Later, I'll cover some of our work on the other components, including detection, ranking, and calibration. There are many applications of this kind of system, including product tagging, visual search, shop the look, clustering, deduplication, ranking, recommendations, and more. This is GrokNet, which we recently published at KDD 2020. It's a unified embedding model for product recognition that leverages multitask learning to train a single computer vision trunk, beating the accuracy of a previous state-of-the-art system by more than double for exact product matching. We achieve this by training on 7 data sets across several commerce verticals and use 3 embedding losses and 80 categorical losses. At the end of the talk, I'll also talk about extensions beyond the system. There's a lot of wonderful related work in production computer vision systems, extending metric learning using classification style losses, learning from noisy data, and multitask learning. Unfortunately, I don't have time to cover this work, so please see our paper for details. For this project, we wanted to ask a key question. Can one model perform all tasks? That is, we want a large-scale embedding that can perform exact product recognition, a medium-scale taxonomy that can predict 1 out of 43,000 search queries, and a coarse-grained approximate classification with 80 categories. With GrokNet, we are able to build this, and I'll show you how. Onto the architecture. This is our large multitask architecture, and I'll walk through every piece in detail over the next few minutes. This architecture supports 7 data sets, 3 embedding metric losses, and 80 categorical losses. On the left, we have a data loader, which samples a few examples from each data set and then constructs a combined batch each iteration. In the middle, we have a deep convolutional neural network with 101 layers. On the top right, we have our predicted embedding, which we use for exact product recognition. And on the bottom right, we have our softmaxes for categories and attribute predictions. Let's dive into the details, starting with the data loader. I'll take a look at how we construct one specific data set in detail, in this case, the home product identity data set. To train our embedding, we need examples of the same product seen in multiple views. We get annotators to look at images from catalogs that we suspect contain the same product. In this example, the 4th image is rejected since it's too zoomed in to verify that it's the same product. Otherwise, annotators draw tight bounding boxes around all matches. While this works very well, the problem is it's very expensive and difficult to collect, and you may be limited in the original source of data. The images may also be too clean, resulting in a system that does not generalize to challenging user images. We solve this by using another fully automatic technique to generate additional training data called weakly supervised learning. Here's how it works. Let's assume that we already have some product recognition system. You could use any existing computer vision features, even if they aren't trained for product recognition. You run it on a bunch of unlabeled images and then assume that any high scoring matches are all correct. You then feed this into the training system shown on the right. So we can open the box in the middle by showing that the 3 steps are exactly the same as I showed in the introduction. You run object detection, extract features, and then match against a catalog. One key parameter is how do you threshold good matches from bad ones? We ran an experiment where we vary this match threshold shown on the horizontal axis. At 0 on the left, we have our baseline performance, which is not using this data. And as you increase the threshold, allowing more matches, you start showing significant improvements up to 27% relative. Beyond this are diminishing returns where you start adding noise to the data set, diminishing the performance. We use this experiment to set the optimal threshold, which gives us the best trade-off between data set size and quality. Back to our architecture diagram, we can now look at a second type of data, search query data. We use anonymized search log data from Facebook Marketplace to automatically create a data set of image query pairs. Here's how it works. On Marketplace, users can browse and search for products, and they can buy from sellers by messaging them. So to collect a data set from these events, we can look for a specific sequence of actions. 1, a user searches for a query. 2, they click on the product. 3, they message the seller. And then 4, the seller responds back. So if all 4 of these events happen in a short time, it's highly likely that the user found what they're looking for, and we can assume that the query is relevant to the image. It's important to note that we do not have access to message contents, and we only know the fact that users interacted with each other. This process generates a data set of 56 million images, each image having a list of relevant search queries. We can then use this data to train one of the heads of our system. Although we're able to generate a lot of high quality data this way, not all the labels are correct. So we actually use some machine learning to automatically clean the data. Rejecting bad labels from the training set improves accuracy by 6.3%. Back to our architecture diagram. Now let's look at the loss functions we use to train the embedding. First, let's consider what properties do we want our embedding to have. On the right, you can see an anchor image and a radius around it showing the distances that correspond to the same product. We want to learn an embedding space such that a single margin can predict the same versus a different product, where different products are far away from the anchor point. To achieve this, we use the arc face loss, which we borrowed from the face recognition literature. It's part of a family of new classification style losses, including sphere face, coast face, arc face, and others. The basic idea is that every product ID has a class center. The current batch has a series of vectors in the embedding called anchors, and you compare each anchor against each class center. Each iteration, you compare every anchor in the batch against every class center from the data set. So importantly, you don't compare the anchors to each other, which gives you a fully global optimization compared to pairwise methods. There's some other details such as temperature scaling and angular margin penalty we don't have time to cover here. The great thing about this loss is that it converges much more quickly than triplet or pairwise losses. The downside is that you have to hold all the class centers in memory, so you're limited by the number of classes you can learn with. There's an alternative new function which we proposed in the paper called pairwise double margin loss, which is a minor extension on prior work on contrastive losses. And you can see from the diagram that the idea is to pull apart negative examples with different class and push together positive examples of the same class. We also have margins to reject small and large distances, which tend to be noise or outliers. The main benefit of this kind of loss is that there's no limit on the number of classes you can have. The downside is that it's slower to train and does not converge as quickly. We can mitigate this, this slow convergence to some extent by computing on every possible pair across every GPU. We use 96 GPUs for training distributed over a network. So in fact, we actually get 96 times more examples than we would if we train it on each GPU. Because we have this global pairwise computation of every embedding on every GPU talking to every other embedding. This gives us nearly a 10% relative improvement in held out experiments. So I have 2 different loss functions, the arc face loss and the pairwise margin. Which one do we use? Well, there's no reason why we can't use both. We use the top 188,000 identities for arc face, 188 because that's what fits in memory, and all of the identities for the pairwise double margin loss. With multiple losses, you just add them together with a weighted sum. So now we have a method of separating the same for different products, but what about the rest of the embedding space? We can still organize the larger distance as well by concepts. In this case, we use our rich taxonomy of 43,000 search queries I mentioned earlier, and we can use that to organize the remainder of the space. We use an additional loss function. I don't have time to cover it here, but we talk about it in our KDD paper, which essentially organizes our products based on ones that have this overlapping search queries shared in common. The next part of our architecture to talk about is the pooling step, which is at the top of the neural network. As a refresher, pooling is a method by which you collapse a feature map at the top of the network down to a single vector, so that you can use it as an input to classifiers or embeddings. Traditionally, you would just average over the spatial dimensions, but we show that if you use generalized mean, or otherwise known as gem pooling, it's been proposed by many other papers, the power parameter P allows the embedding to concentrate on salient parts of the image for each feature. In our case, this gave us a 26% relative accuracy boost in held out experiments. The last part of our architecture to talk about is the embedding itself. We're using a 400-dimensional embedding, which uses 1.5 kilobytes to store per vector. This does not work at Facebook scale when you have a very large number of photos you're searching over. We address this by compressing our embeddings by a factor of 50 down to just 256 bits using a system called Catalyzer, also developed at Facebook AI. Surprisingly, we're able to do this without losing any accuracy, which suggests that there may be further gains in the future. The basic idea of Catalyzer is to make the best possible use of the compressed embedding space by spreading out the vectors from each other so the whole volume is used. You should read the paper for more details. It's at the bottom of the slide. To summarize our KDD work, we presented a new unified architecture. We showed how we train on a very large number of data sets and tests at the same time, and we more than doubled the accuracy of the previous production system. Since that publication, we've actually made several additional extensions, resulting in a further 40% relative gain in performance, and I'll cover some of them here. One of the biggest data-related challenges is that users delete their data over time, and we need to immediately remove it from our training set as they do so. This means that our training and evaluation sets will shrink over time, and we address this using knowledge distillation, using a previous version of the model to supervise the next version. Using a Euclidean distance loss function on the pool 5 features, we're able to get a 13% relative improvement compared to a model trained without distillation loss, even though we only use 60% of the training data. When deploying the model, we also quantize the model end to end, which gives us a 2.5 times speed up over the baseline meaning that every layer runs in floating point. We're able to do this while we're training over 98% of the relative accuracy. We've also done significant work on other stages of the pipeline. Here we're showing the object detection step, which is the first step you do when you first get an image. So at Facebook for object detection, we have many taxonomies. For example, one includes fashion, another one includes home decor and vehicles, and some others. And we've developed a new multi-head detector architecture, which can handle all of these overlapping taxonomies by having different output heads on the detector for each taxonomy. Normally in a detector, you have a single output head with a single softmax. We also map the final results to a single foreground category, since the GrokNet model, which happens later in the pipeline, repredicts the category. And we find that the GrokNet category is more accurate than what you're able to do earlier in the object detector. Compared to our previous system, which had one detector per taxonomy and then unified together, we're now able to detect over 40% more boxes per image. Out of that, it's interesting to note that we got a 5% gain in average precision measured on this one foreground category, just from calibration. And this is a result of having a more accurate relative score between categories. It's something that I think is not talked about enough in object detection work overall. There's a lot of work as well to be done at the matching step. This is after GrokNet. Can I talk about it a little bit here? So in the product recognition pipeline, after the retrieval step, we do re-ranking, which is reordering the results using additional feature. The baseline would be just to use regular distance on the embedding. With just 5 scalar features and a gradient boosted decision tree, we can improve the results by 7 or 21% relative, depending on whether or not we're searching within just one retailer or across all of them. So these features include things like the embedding distance between the query image and the candidate from the retrieval, or the bounding box area. We find that small bounding boxes are more likely to be noise or background or contain bad products. And so by adding this into a re-ranking model, rather than just putting a hard threshold, we can have a system that intelligently learns that for small boxes, for example, you need a really small embedding distance to have a confident result. You can also include things like the category similarity into this model. It's really quite powerful. Finally, we calibrate the model. So that gives us a configurable knob to decide between precision and recall. To get this data, we ask annotators to judge how similar the result is in this product recognition system. We ask them to just tell us, are the two products related? But are they a duplicate image? Are they a same product, different variation? They could be visually similar where they can or cannot tell if it's the same. Or maybe they're just the same category or they're unrelated. So it's a 7-point scale, and you can see in the legend on the top right, the different colors corresponding to the different similarities. And then we plot the different similarities as a histogram over the embedding distance. So what you'd expect is that for a perfect system, exact matches would have very small distance. So that's the red curve of duplicate image. And then all the way to the right of the purple image of unrelated images, you'd want them to have a high embedding distance. And so you can see that our system does do a pretty good job of separating out these curves. And beyond GrokNet, we did it on the next internal release, including knowledge distillation and some of the other things I've been talking about. And we've been able to separate the curves significantly more. And so this is just one way of looking at the notion of how good is it. Of course, you can also measure things like precision, recall, accuracy at 1. But I like this visualization because it's a better breakdown of more nuanced similarity. We can even calibrate every category separately, since we find that different parts of the embedding space are more or less dense depending on the category. And this gives us a 20% relative recall measured at the same precision. The essential idea is that you have a different calibration curve per category, or equivalently, you could also input the category system into a re-ranker that then outputs a single score. The main idea is that somewhere you take into account the fact that category has an impact on what embedding distance should be interpreted as a match. So now to some experiments and use cases. So let's evaluate our system on a real scenario. We went to furniture stores and collected 2,000 photos ourselves. We then manually associated these photos with retailer catalogs to create a ground truth. You can see that this captures a wide variety of challenging examples and scenarios, with some products in the foreground and others in the background. We also have other test data sets for fashion and vehicles and many others. On these data sets, our new system at the time of GrokNet was twice as accurate as the previous system. And this is a combination of all of our architecture innovations, data sets, loss functions, and we're really proud of this win. We think it's also a fair comparison to the previous systems, since it's actually the same architecture and number of bits, and all of these systems were developed at Facebook. So the system before GrokNet, as well as GrokNet and later versions. A lot of the gain comes from the fact that we're now explicitly optimizing the embedding for exact match, as well as using many data sets and losses at the same time. While the previous system before GrokNet was trained only with large-scale search query data with a single multi-label loss. Here's a breakdown by data set. You can see that across all the data sets, furniture, fashion, vehicle, and overall, we improved by a large margin. The last data set is for search queries. We were tied with the old system, but it's not too surprising since the previous system was only trained on this data set with just search query data. Since GrokNet, we also have we continue to launch internal releases. We have a V2, a V3 beyond that. And we're able to show a 14.3% and later a 40% relative increase on accuracy on these internal data sets. The insights that I mentioned earlier around object detection, re-ranking, et cetera, drove these step change improvements. Although we use the system in many places, I can talk about 3 examples publicly in this talk. The first is marketplace search. We use GrokNet to automatically augment every product listing behind the scenes with additional metadata. This helps people find and browse products, improving the user experience. We measured a 9% relative gain in search relevance quality, meaning the percentage of sessions where all top 10 products are correct in the search results. The second place is in marketplace integrity, where we use these features as a baseline for classifiers to help better identify violating products on marketplace. And the third example is in clustering. So we use our embeddings to predict which images are duplicate or in near duplicate from each other. And we can also in particular leverage those calibration curves I mentioned, where we have a good understanding of how similar do the embeddings need to be before it's duplicate or not. We show a 76% relative gain in precision measured at 50% recall over the previous system. This is because our embeddings are explicitly trained to have this property. I'm excited to see where we can go from here as a research community, continuing to push the scale and accuracy of these systems. Thank you so much for your time, and please don't hesitate to email me at seanbell@fb.com with any questions or happy to discuss or collaborate. Thank you so much.